All right. Also, is it hot in here? Or?
Just you, Marissa.
Just, I'm like insanely hot. Anyways, any questions before we get started?
I have a question about the activity series hub. So the very back page, we can, I guess, do this offline also. I don't know where my lab is. But there was a question about what's the oxidizing agent and which is the reducing agent. And so I guess can you just provide some more clarification about when you have an equation like we had on the back page of the
I can try to pull it up too.
So 4 aluminums plus 3 O2s yields 2 Al2O3. And so provide some additional clarification about the oxidizing and reducing agents in that equation? Because I got it wrong and I don't really.
Okay, so who's getting oxidized? So let's start with that.
So,
What'd you say? The aluminum? Yeah, so the aluminum is getting oxidized, right? So it's losing electrons, but then if it's getting oxidized, that makes it the reducing agent then.
okay.
And is that what I marked? Because sometimes, I mean, I'm known to make errors. So yeah. So then this would be the reducing agent, and kind of the reducing agent supplies the electrons.
Okay.
And then it should really be, I wrote that wrong, because it's the aluminum 0 species. So the aluminum metal species is the reducing agent. So you don't want to say, right, aluminum 3+, because that's your oxidized product, but you want to say your aluminum metal was your reducing agent since it got oxidized, but then it's supplying the electrons to the oxygen.
So then the oxidized, so it's the reducing agent,
Yeah,
and it would have been just Al?
yeah. So aluminum, I should put, you could put a solid there to clarify that that's like the metal state of it.
Okay.
And then the oxidizing agent, so usually if you see like some sort of combustion reaction and you see oxygen, that's like your easy, oh yeah, that's probably my oxidizing agent because it's oxygen. But you could see, okay, oxygen goes from 0 to 2-, so we know that oxygen was reduced, and so our oxidizing agent then is the oxygen. It's the one that gets the electrons. And again, you want to put the O2 species, not the final, like O2-.
Got it, okay. Thank you.
Any other questions? Watching the chat too. So I wanted to go over a couple of things and just kind of review some reactions. We'll do some product prediction, and then we'll look at this demo up front as well. But I wanted to start with, I found this graph, oops, and I thought it was helpful, hint, hint, for your quiz, because there's some quiz questions, and when I was kind of looking at it and reading over it, I thought maybe they're kind of tricky, and I don't want people to get too confused. And so let's kind of review what we're looking at and what we're talking about with this functional group isomerization. And so what we kind of find is a lot of these groups are isomers of each other. So remind each other, what are isomers again? Yeah, so in case you didn't hear, so same chemical formula, but different bonds or different connectivity. And so you'll kind of see what I'm talking about when you get the quiz. But what we find is, so looking at like ethanol then, so that means an alcohol and an ester could potentially be isomers. And so that's one example of that is shown here. So there's the ethanol form. And again, I'm just kind of emphasizing that your OH is terminal in the alcohol form versus the ester, where now it's the oxygen's just in the middle and it's not connected to a hydrogen, but then notice, right, same number of carbons, same number of hydrogens, so these would be considered isomers. And so that means that aldehydes and ketones could potentially be isomers. Again, the aldehyde, and remember for naming, those end in that AL ending. So just kind of keep that in mind. And they have that H on the end, so the C double bond, O, H on the end for the aldehyde versus the ketone, or it's in the middle. But again, same situation, so you could potentially have isomers, so 3 carbons on each of these. And then same number of hydrogens, so 6 hydrogens, 6 hydrogens. And then last ones that can be isomers and the isomer pair would be a carboxylic acid and esters. So again, carboxylic acid, we recognize it that it has that COH there at the end, and of course next to our C double bond, and versus an ester where it's in the middle there. And so again, same number of carbons, so this is a 3 carbon, 1, 2, 3, 1, 2, 3 carbons, 6 hydrogens again, and then 2 oxygens for each one. All right, so we feel comfortable, kind of recognize which ones are similar to each other. All right, let's do some reaction prediction. All right, so write the product you would expect from this. Oh, just write the product.
What is the H2 and the PD?
You should know.
Okay, well, I know.
So what's,
I mean, I understand it's hydrogen and palladium, but.
yeah.
So what are, I don't understand what you're looking for here.
Oh, so just see if you can look back in your notes then and like maybe you can find some inspiration. So we're just reviewing kind of common reactions, so going back all the way to like alkenes and organics, kind of in preparation for the final. And if you remember that palladium was a catalyst, I don't know if that jogs anything.
I have a guess for the first one. It's going to, the palladium as a catalyst is going to break out the double bonds and put the two hydrogens onto the chain.
Yep. And so this would be your product. And so maybe you're seeing the insights of to why OCHEM is difficult. So unfortunately, right, you just kind of have to memorize all these reactions and kind of see, oh, I have an alkene. And then you have to recognize, right, you have hydrogen. And we could have used a platinum catalyst. So it's either platinum, palladium catalyst is commonly used. And just like Mon said, that would break the double bond. So that's, again, called a hydrogenation. Or it'd be under the category of addition to alkenes. And does anyone want to name this chemical? Watching the chat too. So you got the butene, but that's all we need to put, right? Because you have 1, 2, 3, 4. So there's your butene. And then we're missing this one little thing. No, 2-butene is correct. So you want to keep it the ene, right? So butene, what would be?
That would be a triple bond.
Yeah, so remember butene is for a triple bond. So let's see if I don't botch this. So 1, 2, 3, 1, 2, 3, 4. Okay, so that would be 2-butene. So 1, 2, where the triple bond starts there, the ine being the triple bond, versus the ene double bond. And then what's the name of the product here?
Butane.
So butane, or sometimes you could put N-butane if you're trying to specify the chain, the straight chain versus anything else. Excellent. So what about this one? Do we need a few more minutes with that? Okay, take a few more minutes. And I'm watching the chat too still. Do we have guesses for this one? We still need more time.
We had you drawing it?
Yeah. At least we have a marker.
I don't know if this is correct, but I know. In this other shot you do?
That is correct. Bring in his markers.
I did it like this so it wouldn't interfere with this double bond. Is that correct?
Do we have another guess?
Yes, I do. It would erase this double bond and boom, would take its place.
So let's start with that. So it's a good start. So it's similar to this kind of hydrogenation. So it does add bromine. So I'll draw just what's drawn on the board. But what's the trick here? And it goes back to the mechanism of these reactions. And there's something missing that we need to indicate. So what do we need to draw or like show here? It actually would be bidentate, but not looking for something else. So.
Would the other bromine would the second bromine have its position here?
No, it's good in this position. There's some information that's missing.
Oh.
Oh, not necessary, or not what I was going for. I like the guesses. What do people remember about the mechanism and kind of think, right, bromine's large. What was the intermediate of this reaction? Do we remember? It was like a special intermediate that we talked about. So let's walk through the mechanism again and see if we can think of the missing part. So we start off again with cyclohexene. And so bromine's going to come along like that. And then it does this where the double bond goes to the bromine. This gets broken. And then we form that weird carbocation intermediate with the bromine. And then, so what happens with that second bromine? So it's hanging around and negative charge on it. So it wants to attack. And then we have this bromine with a positive charge. So that's that weird carbocation intermediate. So that's positive, not good. But then what do we say about how the bromine has to attack? So not the other bromine, but so the bromine's there, right? So bromine's large too. It's occupying a lot of space.
Is it attached to the other side?
No, it's one in the one too, but it's something.
Wild guesses here.
So if we look at this, so this is, it has 4 different things attached to it. So we have our bromine, and then 1, 2, 3, 4, 5 of the ring versus 1 of the ring, kind of. So this, and then this also has a hydrogen, so don't forget hydrogen. So what is this called with 4 different things attached to it? you remember the name for that. Talked about it. It had to deal with like the handedness. So what was that called? You had the carbon with 4 different things attached. So that's a chiral center. And so when you have a chiral center, you have to indicate chirality. Or if you don't, so like how we have it drawn here, right now we're showing that chirality doesn't matter, but it does. So going back to the mechanism, why we have to show stereochemistry for this chiral center is, so now you have this bromine, and so it's kind of sitting on top, at least how we've drawn it, right? We could also draw it from the bottom. It would be the same thing rotationally. But the point is that the bromine then has to attack from the other side. And so when it attacks from the other side, so it's going like underneath, that gives it the trans stereochemistry. And so you have to draw that and show, so you had your bromine, then, so let's say, right, how we drawn it, it was floating up top with our carbocation, then your other bromine comes on underneath, and so that means this one, because remember this cyclohexene is kind of like a plane, at least where we're looking at. One bromine's on top, the other one comes in on the other carbon, and so we have to indicate this for this one, and that's because the cis isomer, and so the mechanism for this one and why it doesn't exist, so cis, and I'll put not observed. So again, we're back at this intermediate, so bromine, oops. So it's up, and you can't have another bromine come on from the top because there's one already sitting there, so it has nowhere to go. So it can't come in, and that's what would have to happen. It would have to come in from the same side to get that cis stereochemistry. So I'll draw the cis one. And that just means, again, same side. And so by rotation, right, you could draw this, so that's still cis. Same thing with this. You don't have to draw it like that. This is also trans. So same thing, right? We're just showing that the bromines have to be opposite sides from one another. And that's back to that intermediate that it just physically can't happen. So no cis observed, only the trans isomer for these halogenation. Okay, questions? Feel better about that? So if you're taking OChem, take notes. This will come up, I'm sure. So this would just be like a halogenation reaction. And so in OChem, you'll learn like different varieties too, because you could do this in the presence of like water as well and do like a bromine and OH addition. You can add HBr across, all the same sort of concepts of this hydrogenation and halogenation. All right, let's do some more kind of review. So I'll put predict the products. But there may be a no reaction. And so I'll put kind of 2 scenarios. You can figure it out. 1, 2, 3, 4. And so this symbol just means oxidation. And then predict the product. And then predict the product after a second oxidation. feel free to chat with your neighbors too. So what's the difference between those two scenarios? What are the products? You might want to name those products too.
Would it, unlike sequencing, or observations, is it when there's an alcohol group, already, is it, will it form another alcohol group at the end of the other end of the chain first, or will it, create that, that carboxylic acid first?
Oh, it's not going to add the alcohol, but slow down before you jump to the carboxylic acid. We'll give people more time too to think about it. How are we doing? on these reaction predictions. So let's start by naming this product. So what's the name of our starting material here? So 1-butanol. And then is this a tertiary, secondary, primary alcohol? So is it a tertiary, primary, or secondary alcohol?
Primary.
So it's a primary alcohol. So do we remember what primary, tertiary, secondary means? Do we need to see some nods, some no? So remember, primary alcohol just means that your alcohol is attached to a carbon that's only attached to one other carbon. And that means it's attached to 2 hydrogens, versus a secondary alcohol is attached to a carbon that's attached to 2 carbons and only 1 hydrogen. And then that means a tertiary alcohol, it's connected to all carbons, so no hydrogens. And so do we remember what the product is then of an oxidation of a primary alcohol? It creates a certain functional group. Oh, aldehyde? So it makes an aldehyde. And so I'll just write aldehyde for a second. So if it makes an aldehyde, can you guess what the name of that aldehyde would be? So you started with butanol. And then, so what's the aldehyde name with 4 carbons, basically? Or if anyone wanted to write the product on the board, you can also do that. So what's the aldehyde name? What's the ending?
So butanol.
Yeah, butanol. Wow, I really can't spell today for some reason.
I can write it.
Let me try that one more time. Butanol. Okay. And so then that would look 1, 2, 3, 4, like so. So our aldehyde. And then, so do we remember what happens if we do another oxidation with the aldehyde?
What happened to the other oxygen?
So 1, 2, 3, 4, the OH here. So this is a, it gets popped off as a leaving group. And then, so this oxygen comes on from our oxidant. And then what happens then with a second oxidation?
Would it make carboxylic acid group?
Yeah, so now it makes the carboxylic acid. And sometimes you could see this done in like 2 steps or like one big step of they'll do like a double oxidation. And that just means that they're taking the butanol all the way to the carboxylic acid form. And so what would be the name? Again, we have a 4 carbon chain base.
Butanoic acid.
So butanoic acid. One, two, three. And so what's the difference now? Yeah.
This is a secondary alcohol.
And so this is a secondary alcohol. And so what happens when you take a secondary alcohol and you oxidize it? What group do you make? So a ketone. And so now it's off to the center here. So 1, 2, 3, 4. And so what's the problem with the ketone? Why can't, or does it undergo a second oxidation? So I see shaking heads, no. So we don't have an H to pop off now. So no more hydrogens attached to it to leave and react with. So now we're stuck here of no reaction. And then so throwing this one on here, what happens with this alcohol under oxidation conditions?
There will not be a reaction.
So no reaction for that one. And again, tertiary, so now no hydrogens or anything. All right, let's do a little bit of naming practice. We'll do simpler ones. So see if you can name these compounds. And so I may not have written them in the most clear way, so you might want to rewrite them kind of in their more stick form. Make sure you get the connectivity. So we'll start with those. Try all three, and then we'll go over them. So give people some time. And so if you're watching online, you can post your answers in the chat too. I'll give people a few minutes. Ask your neighbor, compare your drawings.
Is that an R in C? Or is that?
Where? Sorry, there shouldn't be any R's. That's a F. So I'm trying to draw like C bonded to F.
Okay.
Are we ready to try the first one at least? So now this one, and so I'm just going to start kind of drawing this in a different form. So we have our CH3, CH2, C, and then Br2, so that must mean that they're both on that one carbon. And H2, just filling that in. All right, so that's drawn a little bit better than what you were given. And so, anyone have a name? Want to go for it?
2,2-dibromobutane.
So 2,2-dibromobutane. So everyone agree with that? So I see mostly nods, and we can go through it, right? So we can find our longest chain, 1, 2, 3, 4. And then bromines have to get priority. So we give them the 1, 2 versus, right, 1, 2, 3. So that's where we get our 2,2-dibromobutane. Excellent. Are we ready for this one? Do we need some more time? Okay, let's at least, I'll draw it in a slightly better form. So we have C, so 3 CH3s attached to this carbon. So what are some names that we could come up? Yeah.
1-chloro-2,2-methylpropane.
So let's see. So let's start with propane. So did you get a structure that looked like this?
I did the priority wrong. I counted. It's one as a carbon, one is actually not. Then it would be 2-chloro, 2-methylpropane.
So I see some nods. So do people agree? Looking for thumbs up in the chat too. And so I highlighted it because either way, it's a 3-carbon chain. So 1, 2, 3, 1, 2, 3. And then either way, right, that doesn't change the priority of chlorine. So it's always a 2, no matter if you go the straight way or this way. And then that leaves us with the methyl. Again, it doesn't matter whether this is your 2-methyl or this is your 2-methyl, but either way, you still get 2-chloro-2-methylpropane. Could there have been another name for this? Anyone get another name or could see another name? What was this group called? You remember what that group was called? So this is a T-butyl or tert-butyl. And so, well, this is its proper IUPAC name, yeah. Yep, so its other name is tert-butyl chloride. I'm actually not sure which one would be more popular. You might see the tert-butyl chloride name more, actually, just because people will recognize that T-butyl group. Excellent. All right, last one here. Do we have guesses on the name? I also didn't rewrite it yet.
I have a guess.
Okay, I don't know if my redrawing helped. What's your guess? We'll go from there.
Oh, I drew it completely differently. What I drew it with that second group out of the main chain. And what I got was 2-fluoroethene hexane. But looking at this would be 4-fluoro octene, 1-octene.
Oh, yeah, and I left off a methyl group. So 4-fluoro.
4-fluoro, 4-methyl octene.
Excellent. So did we get this? And this one was kind of tricky just because it was drawn funky to begin with, and I did that on purpose. And so it's just about finding that longest chain, so you kind of have to follow this connectivity and recognize that this one's on here, and then this is connected to that carbon. Questions? How are we feeling on things? So we'll do more practice on Tuesday, so probably more like naming and reaction prediction practice, but I'm going to pause for now, and then we'll try to do our demo and see how this works. So let's shift gears. And well, let's actually look at what reaction we're doing today. So let's go back. And so we have everything here for nylon synthesis. And so let's just go over what we're doing. And so we're looking at the synthesis of nylon, so exactly right what like pantyhose are made out of. Well, I don't know who wears pantyhose anymore, but in fashion. And we're using 2 different chemicals today to do our reaction. And so for one of them, we're using adipyl chloride. And so I'll draw that out. 6. Oops. So there's adipyl chloride. And then we're reacting it with hexamine diamine. And I should have said that this is nylon 6,6 specifically that we're doing. And so the other chemical is hexane, 1,6-hexane diamine. And so from your naming skills, you can tell, right, 6 carbons, 1,6, 2 amines, 1 on each end. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And so that will then do similar mechanism to what we've been looking at, right, with carboxylic acids. So we have our amine again, attack here, right, double bond goes up, and then as it reforms, that's when the chlorine gets kicked off. So exact same mechanism. And so that will give us our nylon reaction. 1, 2, 3, 4, 5, 6. And so, of course, make the amide bond there. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There we go. And repeating. And so this is your new monomer, your repeating units, so those two go together. And then obviously you can continue linking them forever and ever to make our polymer like we're about to do. And so we'll see how this works. Let me try to adjust my camera for the online people. Okay, try to keep that in view here. Let me just have my instructions just in case. All right. So step 1, if you need to get closer in class, you can. And so if it starts like smoking a little, it's just like HCl gas. And if it gets too nasty, I may like run it out of the room and just stick it in a fume hood for a little bit. So that's what will be happening. So first step, we have, and so this is the only part I'm slightly nervous about, is I haven't used the solid hexane diamine before. I usually just purchase it as a solution. So I have to make a 5% solution. So we'll see how that works today. And so I have 8 mils of it already prepared, 5%. And so I'll pour that into a beaker. And then I'll add to it, so 6 drops of 6 molar sodium hydroxide. So 1, 2, 3, 4, 5, 6. And 1 more. And then so now I have another 50 ml beaker, dry. And so that just means you don't want to, wet it right before using it. So don't clean it. And so now I'll mix. So I have a little baby iPad if I can open it. Now I have this baby little pipette here. So this is a 1 ml pipette. I need half a mil, so I'll use this. And so this is my adipyl chloride. Oh, before I do that though, I forgot a pipette for my cyclohexane. So let me run and get that. then I just have cyclohexane. So let me get 8 mils of that. So I just mix 2 organics. And so now I'm just going to carefully pipette this cyclohexane solution into hexane diamine. I'm just kind of pipetting it on the side. And now you can get closer. It's already starting to form. Put it better on the camera. And so if you got close, you can see that there's a little bit of gas, and then you'll see that the 2 layers are obviously forming, since we have a water layer, because again, I prepared the hexane diamine as an aqueous solution in water. So more hydrochloric acid gas being involved. So I'm just adding it slowly so we get those 2 layers preserved. Almost done adding this. And so now we should see the film. So does everyone see the film kind of that's formed here? So yeah, get close. You can kind of see it on the camera. If you're watching online, yeah, so you can see it looks kind of milky. So yeah, it's got that like a weird film. So that's the nylon. And so let's see if I can do this now. So I should be able to grab it. Come on. So you're watching, so I can grab it. And I'm going to see if I can twirl it like spaghetti around my forceps. So I should be able to just keep drawing it so you can see the polymer. Should keep going for a while. So this is just nylon. Still going. And so right, we can tell it's a polymer because it's just this nice chain. Keep going, keep going. Oh, okay, so I broke it now. Oh. I think that's about the end of it. So I could try to grab some more, but that is just nylon right there. So super easy. And so now what we could do is kind of wash this nylon, and yeah, you could take it home, look at it. So yeah, that's how you make nylon. Sweet, and it wasn't too smelly, so I'm happy about that.
It's always got that weird tube of the bottom liquid in it. Because it slurps it up with the vacuum.
All right, questions, comments? Should we take our break now?
You want to squeeze it out?
Yeah, I'll have to squeeze that and rinse it if you actually want to touch it. So yeah, we'll stop here then, and so I'll take that and probably rinse it, squeeze it, and then you can look at it while you're taking the quiz. So I'll have to wash it so it doesn't have any HCl residue hanging out on it. And then, of course, don't forget lab today. So super fun lab, aspirin synthesis. Just don't eat the aspirin because it's not going to be pure enough.
Unless we do really, really well.
Yeah, you just don't have an NMR to test it. Like if you had an NMR, it could be like, bam, that is beautiful. Then I'd be like, maybe. But the best you have is a melting point, which melting points are already finicky.
Hey, it might not have been undergrad, but grad students produce some of the best chemical purity on the planet in drugs.
Oh, I'm well aware of that, yeah. I went to a school famous for that, so. All right, I'm going to stop the stream, so thank you all.